Okay, now we're going to be looking at problems where things are at an angle now. Okay, so we've got this question here. So here we're told one end A of a light elastic string AB of natural length 0.6, modulus of elasticity 10, is fixed to a point on a fixed rough plane, inclined at an angle theta to the horizontal, sine theta is 4/5. Ball of mass 3 is attached to the end B of the string. Coefficient of friction is a third. The ball rests in equilibrium on the point of sliding down the plane. Okay, so we need to find the tension and length of the string. So what's going on here? So hopefully this one should be a more familiar sort of example, a more familiar situation where we've got a slope. Okay, so I'm going to draw a nice slope here like this, right? And the angle is theta. Okay, right, so here now we've got a string on the slope, right? Now we got now one end A is fixed. Okay, so let's say A is there. Okay, there we are. And so it's the string. Well, the other end of the string will have a ball. Okay, that'll be the point B, right? That's AB. And no, it's going to be the other way around. It's going to be the other way around. The ball needs to be down. It needs to go down the slope because we're told the ball is sliding down the slope, down the plane, right? So actually what's going to look like is A is going to be the fixed point up the slope, and then the string's going to hang down, and then the particle at B. Hopefully that made sense, right? Because I'm told that the ball is sliding down. Okay, so the ball needs to be at the further end of the string, okay, for this to make sense. Okay, hopefully happy with that. Now we need to add our forces on. Well, firstly, the ball has a mass of 3, which means the weight is going to be 3g, which is going to act downwards like this. But of course, with these sort of problems with slopes, again, we need to split up the weight like this. So this is also theta, so this is going to be 3g cos theta, and that's going to be 3g sine theta. Okay, so that's the weight. There will also be a reaction force, right, because it's on a surface. So there we are. Now, let's discuss tension. Okay, now think about it. The particle wants to move down, so that means the string is being stretched down. The string is going to be stretched further down, which means the tension is going to act up the string. Okay, so there we are. Then lastly, we have friction. Now that's the friction of the particle. Now again, if the particle's moving down, friction acts the opposite way. So friction will also act along there upwards. And that's all my forces. Hopefully happy with that. Right. Now, I'm going to note that mu is a third. Okay. So that's everything. Now we need to find the tension here, the tension in the string. So really at this point, once we've labelled our forces, hopefully again you're happy with this diagram here. It's just standard procedure. We've dealt with this even in the last chapter, in the work and energy and power chapter, and even at A level in normal maths. What we can do is start to resolve stuff. Okay. So firstly, what I can do is firstly resolve in this direction, so perpendicular to the slope. So firstly, we got the reaction force acting that way. Then the opposite is going to be the 3g cos theta. Okay. And there is no acceleration involved. So it's going to equal 0, so therefore r is 3g cos theta. Okay, but we want an actual number for r, So that's going to be 3 times 9.8 for G. But we need to find something for cos theta. Now, we don't have an angle for theta. We only know what sine theta is. Okay, that's 4/5. But hopefully you're familiar with how we can sort of obtain cos theta from this. We don't need to find theta directly by doing inverse sine. What we can do instead, the more sort of proper way, again, if we draw a triangle, the same angle theta, but if we consider SOHCAHTOA, well, if we stare at it, this numerator 4 has to be the opposite, which would be here, and then the hypotenuse would be 5. Okay, therefore we can deduce the adjacent side by Pythagoras. So root of 5 squared take away 4 squared, it turns out to be 3. That's my adjacent side then, right? So therefore cos is going to be adjacent over hypotenuse, so that's 3 over 5, and there we are. So cos theta is 3/5. Okay, and so now we can deduce the reaction is going to be 17.64. okay, now immediately, because I also know the coefficient of friction, I can work out the friction because I know that F equals mu r, right? Therefore F is going to be 1/3 times r, and that will get me 5.88. And there we are. Okay, so that's my reaction and friction. Then I can lastly find the force T here by now resolving along the plane, so in this sort of direction. So my force is sort of up the plane, up the surface, up the slope. That's going to be the force T, right? And the force F, the friction, they both act up the slope. So there we are. So T plus F. Then the sort of force in the opposite way is again this 3g sine theta. Okay. Hopefully you're familiar with that from probably other examples you've done before. Again, that's going to equal 0. There's no acceleration here. Okay, so if I rearrange this, so T is going to be 3g sine theta minus F. Okay, so T is going to be 3 times 9.8 for G times sine theta, which is 4/5. Okay. Take away F, which was 5.88. So therefore T, my tension, is going to be 17.64 newtons. Okay, and there we are. Okay, then I need to find the length of the string. So again, the whole length here. Okay, so again, the string is being stretched down. Okay, which means it's going to have some natural length and an extension. So let's say, there we are. Let's say this is my natural length, L, and then my extension, X. Now I know my natural length, I'm told, is 0.6, and the extension, X, I don't know, but I can work it out. How can I work it out? Well, this is where Hooke's law comes in. So T is lambda X over L. I know T is 17.64 is going to equal lambda. The modulus of elasticity is 10 times X over 0.6 for the natural length. So therefore I can solve for X. So that means 10.584 is 10x. Therefore X, my extension, is going to be 1.0584 meters. Okay, but they've not asked me for the extension, they've asked me for the length. So that's the total length. So that's this whole length here. So hopefully then you can see the total length of the string is going to be the natural length 0.6 add the extension 1.0584. So that would be 1.6584. And there we are. Cool. And then we got this final part here. We're told if mu is greater than a third, without doing any further calculation, state how your answer to part AII would change. So how would the length of the string change if the coefficient of friction is bigger? Okay, there's sort of two ways I guess you can think of this. You can think of this just mathematically. So if mu is greater than a third, okay, well, what equation involves mu? Well, it's F equals mu r, right? Where did I do F equals mu r? Here. F equals mu r. So if mu is bigger, that means the friction will be bigger, okay? Then F would increase. So my friction force. So then if F increases, well, then my tension here, my tension equation here subtracts the F. So if I'm increasing F, I'd have to decrease the tension, right? So T decreases because we're decreasing by a larger number, because we're subtracting by a larger number, right? And so T decreases. Okay, well, again, then via Hooke's law, X would decrease as well, okay? But X is the extension, so the extension is decreasing. That means the total length decreases. So therefore our answer will be lower, okay? That's from a mathematical lens, right? But sort of the logic behind it, right, is, again, if the coefficient of friction is bigger, that means the slope has more friction, right? It's more sticky. So if you think about it, if the friction is bigger, there's more opposition to the particle moving, so the particle won't move as far. Well, therefore, if the particle doesn't move as far, then it won't extend the string so much, so less length. And there we are. Okay. Then we've got this question here. First of all, I'm just going to draw out the diagram to be a bit bigger. Okay, there we are. So we have an elastic string, natural length 2, modulus of elasticity 98. The mass is 4. Basically, pretty much everything's on the diagram. So they want me to find the value of theta firstly. Okay, so the angle theta here. Now, what's happening here is, this is my string here, right? Okay, and obviously this is my fixed point of the string. But you can see the difference with this example compared to the others is it's not completely vertical, so it's not hanging down completely like this, or not like this. It's sort of at an angle, right? So we can do pretty much the same things, but we're going to need to split up the forces horizontally and vertically. Okay. Now, okay, what forces are happening? Well, firstly, again, we've got a particle at the end here. The particle has a mass of 4, which means there will also be a weight of 4g down like that. Okay, we need to add that on. Well, obviously, we're also given this horizontal force of 28 to the right. Okay, now the last force is, as you guessed, the tension. Now, again, this is my string. Okay, and so as you can imagine, the particle here is stretching the string like this. It's stretching the string down, which means the tension in the string will then have to act up it. Okay, so my tension here, T, acts up the string because the string is being stretched down. Hopefully you can see that, right? So those are my forces. But again, this so then the tension force is at an angle. Okay, which means we're going to need to split it horizontally and vertically. Okay, so if I just literally isolate and only draw the tension force like this, so if I only just focus on T, okay, well, if I want to go up the string in this direction to split it up horizontally and vertically, I'm first going to have to move to the left, then up. Okay, hopefully you can see that. So then if I use SOHCAHTOA, I can now deduce that firstly this side to the that's going to be, well, it's the opposite, right? It's the opposite, so it's going to be T sine theta. Okay, then for this side here, this is my adjacent, that's going to be T cos theta. Okay, so here what I've done now is split it up horizontally and vertically, right? So hopefully happy with that. So I've split up the tension at an angle. I've split it into a purely horizontal and vertical sort of component. Okay, and so there we are. Okay, I'm going to add that onto my diagram. Okay, and that's the whole idea. That's the idea of these sort of questions. You want to split up the forces in this way. So that's going to be T sine theta here, and then T cos theta up here. Okay, I'm going to get rid of this here now. So that is my fully labelled diagram. Okay, those are all the forces I need to consider. Okay, now what I can do is resolve. First, I'm going to resolve horizontally, so to the right and left. But firstly, my force to the right is 28. That's going to equal my force to the left, which is T sine theta. Okay, again, it's an equilibrium, which means all opposite forces equal one another. Okay, so therefore T sine theta is 28. I can also resolve up and down. And so if I look up and down, well, firstly, T cos theta here acts up. And that's going to equal the downward force of 4G. Okay, and there we are. So, okay, if I simplify this a bit, if I bring it down here, I have T sine theta is 28, and I also have T cos theta is 4G. Now 4G, if I put G to be 9.8, that's 39.2. Okay, so there we are. These are the two equations I get from resolving. Now, I need theta, okay? I need theta, okay? So it's sort of like simultaneous equations, right? How am I going to get theta on its own? I need to get rid of the t. Well, what I can do, right, if I call this equation 1 and equation 2, hopefully you're thinking of some trig identities, perhaps. What I can do to solve for theta is I can divide the top equation by the second, and so doing that I have T sine theta divided by T cos theta equals 28 divided by 39.2. And so what we get then is, well, the t's cancel, so we get sine theta over cos theta. But what's sine theta over cos theta? Well, hopefully from year 1 pure maths you'll remember that tan theta, right? So tan theta is 28 divided by 39 over 0.2, and that would be 5 over 7. Now we can easily get theta by doing an inverse tan. So inverse tan of 5 over 7 gets me 35.54 degrees. And there we are. That is the value of theta. Okay. Then for part B, they want me to find the length OP. Okay. Now I should say again, O is here and P is there. So in other words, they want the length of the string. Okay, because the string is OP. Right. Well, actually, if we go back to our simultaneous equations here, I know what theta is now, so I can find T, the tension. I'm going to sub it into the first one. So T sine theta, T sine theta is 28. Therefore, T is going to be 28 divided by sine theta. But I know theta is 35.54. So therefore, I get T to be 48.17. Okay. And there we are. Now, why is the tension helpful? Okay, well, hopefully you're thinking, well, the other thing I can use is Hooke's law. So T is lambda x over L, right? Now, again, T, which we just worked out, is 48.17. Now, lambda, the modulus of elasticity, is 98 times x over the natural length, which is 2. Okay. So I can solve for x, right? So x, the extension, I can solve for that. So that means 98x is 96.346, blah, blah, blah. Therefore, if I divide by 98, I get x to be 0.983 meters. Okay. And there is x. But that's my extension. So therefore, the length of the string, which in other words is the length O to P, that's going to be the natural length added with the extension. Now again, the natural length is 2, so that's going to be 2 add x, which is 2 add 0.983, which would be 2.983. And there we are. That is my length there. Cool. So yeah, so that's sort of the main idea, right? So when we got a force at an angle, so if we got a tension at an angle, we can split the tension up in this way, so horizontally, vertically, right? Okay, so hopefully happy with that. Okay, so we've got this last question here. So here we're told an elastic string of natural length 2L, modulus of elasticity 4 mg, is stretched below 2 points A and B. The points A and B are on the same horizontal level, with AB equal 2L. Particle P is attached to the midpoint of the string and hangs in equilibrium, with both parts of the string making an angle of 30 with AB. Find in terms of M the mass of the particle. Okay, so it's quite similar to the last question. It's going to be the same sort of diagram. So again, we're told these points A and B are on the same horizontal level. So let's say A is here. Then B would be over here on the same level, okay? And so then what we're then told is the particle is then in the midpoint here, okay? And furthermore, the particle is going to be hanging underneath the line like this, okay? How do I know this? Because I'm told the particle makes an angle of 30 with both parts of the string. So what's happening there is the string is being stretched down like this, okay? Very similar to pretty much the same as the last example, right? And the angle it makes with the line AB either side is 30. Okay, so that's the setup here. Okay, again like a slingshot. Okay, I'm going to add my lengths in because I know that AB is 2L. That might help. There we are. Okay. Okay, then in terms of angle, in terms of in terms of forces. Okay, so firstly, again, I got my particle, the mass. But they told me to find the mass of the particle. I'm gonna say the mass. I can't say m. Okay, they've already used m. That's annoying. I'm gonna call the mass k, which means the weight of the particle is going to be down here by kg. Okay. Then in terms of tensions, but again, the same sort of scenario. The string is split into these two sides here. We've got the string AP and the string PB again, right? But they're what's special about this one is they're actually kind of equal, because the particle is in the midpoint. Okay, which means the tension forces, again, the tension forces is going to act up the string here because the string is being stretched towards P down here. Okay, and likewise, the tension for PB is going to act up because, again, it's being stretched down. So there we are. The tensions are actually going to be equal because it's symmetrical in this case. Okay, because P is in the midpoint. And the so the strings are exactly half and half in this particular case, okay? And the forces will and so the tensions will be balanced, so they'll be equal. Okay, so there we are. Now, if I now further do this again, what am I going to have to do? I have my tensions, but I'm going to have to resolve them and split them horizontally and vertically. I'm going to have to do that. To do that then, if I consider this, well, firstly, if I resolve this force here, the tension acting up here, I'm going to have to go up and then to the left. Okay, so then this is going to be, this side is going to be T sine 30. And then this is going to be T cos 30. Okay. And then if I do the same for this tension here, well, actually, I'm going to go up and then to the right. Well, actually, if I go up, it's also going to be T sine 30. Okay. And then to the right, it's going to be T cos 30. Okay. So hopefully happy again with how I split up the two tensions here into horizontal and vertical parts. Again, identical to the last question. Okay, so hopefully happy with this. These are all my forces. I can actually also, because it's in the midpoint, I know the whole length is 2L from A to B. The midpoint is L each side. So there we are. Okay. So now let's resolve. Let's firstly look up and down. So up and down, well, firstly, I've got my two forces up. So I've got T sine 30 and another T sine 30. Actually, I could simplify this to just two lots of T sine 30 because they're the same, right? 2 T sine 30 is going to equal the downwards force of kg. Well, I can actually simplify this because I know that sine 30 is a half. 2t times a half is 9.8 k, because g is 9.8. So that means now 2t times a half is just t. So t is 9.8 k. And there we are. And then we can perhaps look at resolving right and left, so horizontally. But if we do that, well, the force on the right is T cos 30. That's going to equal the force on the left here, which is also T cos 30. Well, that doesn't help us. It doesn't tell us anything. But it does tell me my forces are labelled right, which is great to know. Also, what this would mean is actually, if you were a bit unsure about the tensions being equal on the left and the right, so if I called this T1 and T2, right, then with this equation, then we would say T1 cos 30 is T2 cos 30. Well, the cos 30s will cancel to get T1 equals T2. So actually, hopefully you can see here then that indeed the tensions on the left and the right side must be equal. Okay. So the only thing I do know really is T, the tension is 9.8 K. Okay, so if I have a tension, then it might be a good idea to use Hooke's law, right? T is lambda x over L. Now, where am I exactly going to use this Hooke's law? Okay, well, what's happening here is, again, I have these sort of two. I got these two half strings together, right? So I got half the string from A to P, and then the string from P to B, and these two make up the whole string. Okay. So what I can do, like with the last example, is just consider one part, right? So let's consider just the part from A to P. Okay. So let's just consider this part here, right? Okay. So I'm only going to apply Hooke's law to the string A to P, right? So A to P. Okay, so again for A to P, I have my tension force T. So that means T, which I know is 9.8 K, is going to equal lambda x over L. Well, the modulus of elasticity is 4 mg times extension x over the natural length. Now, as I just discussed, we're only dealing with one half of the string, okay, from A to P. So we're going to be halving the total natural length, because remember the whole string again goes from A to P, then P to B. I'm only doing A to P here, so it'd be half the natural length. Okay, so it would just be L. So therefore 9.8 K lots of L is 4 mgx. Okay. And so there we are. Okay. I'm going to need to find the extension x. Okay. I'm going to need to find the extension x for the string A to P. Now again, like with the last example, this length here is the total length from A to P. So this is the total length of the string A to P. So if you want to find the extension of the string from A to P, we're going to need to find this total length here. So let's consider just the triangle here, right? If I do the triangle here, then I'm going to copy this down here. So this is going to be 30. I want to find this length here. Okay, what is this length here? This is A, that's P. This is a right angle. Okay, so hopefully happy with that. So there we are. So I'm going to be using some trig here. But what I also know again is that this length is L. So here is L. So now I'm in a position where I know an angle and a side. So if I use SOHCAHTOA, okay, well the side AP here, that is my hypotenuse, because that's facing the right angle. And here, the side L is my adjacent. Okay, so SOHCAHTOA tells me that cos 30, so cosine, is adjacent. So that's going to be L over the hypotenuse, which is what I want to work out, right? In fact, I'll make it more clear. So that's going to be the adjacent over the hypotenuse, which is L over that, which means the length AP, that's going to be L divided by cos 30. If you just rearrange this, right? Okay. Okay, so therefore AP, the length AP, well, it's L divided by cos 30. So if we divide by cos 30, we get AP is 2 root 3 over 3 lots of L. Okay, and so there we are. That is my length from A to P here. Okay, 2 root 3 over 3 lots of L. Okay, hopefully happy with that. So that is the total length of the string A to P. But that's the total length. I want the extension of that string, X. So therefore, the extension, okay, the extension X is going to be the total length, which was 2 root 3 over 3L, take away the natural length, which was just L. Okay, that gets me my extension. If I work that out, that's going to be 0.155 lots of L. Okay, and there we are. So now I could substitute that value of X into here. So that means 9.8k lots of L is going to be 4 mg lots of X, which is 0.155 L. Okay. So that means 9.8k L is going to be 4m times g, which is 9.8, times 0.155 L. Now what I can do, I can actually divide by 9.8 lots of L. So I can cancel out 9.8 and L from both sides. So that means I just get K to be 4m times 0.155. And so there we are. We can then deduce that K is going to be 0.62 lots of M. And that is my answer. So the mass, which is K, is now in terms of M here. Okay. And there we are. So again, that's the whole idea. Okay. Like with the last example, we can just consider one side, A to P. So we can just consider that string A to P there. Okay. And then we can use it, then we can work out the length using SOHCAHTOA and then go from there. Okay, but that's it. Hopefully that has helped. But I'll see you next time.